All right, good afternoon, everyone. Welcome to another lecture where we study light, its propagation, scattering, and radiation. As always, let's begin by recalling what we talked about the last time 1 week ago. So the last time we talked a lot about butterflies and wonderful photonic crystals on their wings and about photonic crystals in general. And actually, let's remind ourselves what we talked about. So let's go back a little bit more and let's remind ourselves what we talked about last 5 or 6 classes. And you should remember that we've been talking about plane waves in different media, in homogeneous media. We talked about what happens to plane waves when they encounter an interface between two media. We talked about different combinations of plane waves, such as Bessel and Gaussian beams. And then we talked about waveguides. We talked about waveguides a lot. We talked about parallel plate waveguides, dielectric waveguides, and surface waves that are supported by interfaces between different media. And in all these problems that we considered so far, we did have some sort of radiation, some sort of plane wave or waveguide mode propagating from -infinity to +infinity across the entire system. And we never wondered where this radiation comes from. This radiation, these plane waves, these waveguide modes, they have to be created by some sort of radiator, by some sort of antenna or electromagnetic source. But last 6 classes, the source of radiation was outside the domain of our interest. We only looked at the radiation itself, how it propagates through the system as a plane wave or in the form of a waveguide mode. And today we're actually going to start looking at the radiation problem itself. We're going to look at how radiation is emitted by source, how it propagates in space, how it forms the emitted signal itself. And next 3 classes, we're going to be looking at that kind of electromagnetic problem where we do have a non-zero, non-trivial source, whether it's some density of charges or density of electric current in the right-hand side of Maxwell's equations, where we previously had identically 0. So this slide summarizes the class of problems that we're going to be studying next 3 classes. And this problem that we're going to look at covers a broad spectrum of structures, applied problems, ranging from emission created by radars and 5G cellular towers, down to really microscopic systems involving some organic or inorganic molecules emitting light in the plasmonic gaps between plasmonic particles and even single molecules or single atoms positioned in a tiny nanogap between plasmonic antennas. So despite the systems that I gathered on this slide, despite the fact that they're completely different and they exist on completely different length scale with many orders of magnitude of difference between them, as you'll see, they're described qualitatively by the same kinds of equations, by the same kind of Maxwell's equations with a source term on the right-hand side. So let's begin with the simplest system, the simplest case of radiation, that is radiation in the free space. So as you remember from I believe it was the 2nd lecture where we briefly covered the radiation problem in electromagnetics without actually solving it. We introduced the concept of the green tensor that for an arbitrary electromagnetic environment characterized by some permittivity and permeability tensors distributed in space, that tensor relates the current density at our origin J to the electric and magnetic fields that we want to calculate in the observation point. Again, this is our local coordinate system. So this is the green tensor. This is the quantity that actually dictates the creation of emission by any source. And today we're going to find a solution to that problem. We're going to find the green tensor of the simplest system, that is the free space. So radiation is governed by the wave equation with the current density on its right-hand side. If we had 0 here, the only non-trivial solutions of that equation would have been plane waves that we already studied. So now we're going to consider free space. Epsilon equals mu equals 1. And we're going to try to solve that equation with some non-trivial current density on the right-hand side, okay? So knowledge of the Green's tensor of the wave equation in any environment will allow us to solve the radiation problem. Once we know the Green tensor of the given environment, we can always integrate an arbitrary current density, and we can obtain the electromagnetic fields, the electromagnetic fields at any point of interest. But first, we have to find this Green tensor. And like I said, today we're going to be handling this problem for the simple situation, free space. Okay, so let's start. Let's try to find a way. Let's find out how to solve this equation. And at the first glance, it is tempting to expand the double curl operator in the following way, like we did with plane waves. So the double curl of a vector is minus Laplacian plus the gradient of the divergence of this vector. And this is exactly what we did with plane waves, and that helps us to obtain the spectrum of plane waves in isotropic media, and it also helps us a lot in waveguide systems. But if you follow this approach, then we'll soon run into a problem, because this time divergence of D does not equal 0, because we have some non-trivial source. We have charges. So this equals actually wrong. This equals the charge density, which is non-zero, because we do have a source of radiation, right? We do have some charges that oscillate back and forth. So this is not 0. And so this guy will remain. We cannot neglect this. And this will make our life very complicated. So we're going to have to find another way to handle this problem. And this is how we're going to do this. Instead of trying to expand the double curl of electric field, we're going to obtain an equation for the vector potential. So instead of electric field, here we're going to plug the vector potential and scalar potential. So electric field can be expressed as minus gradient phi minus dA over dt. We're going to plug that into the wave equation. And if you do this, we'll obtain this, which is still quite complicated. That doesn't make our life easier, because now instead of just electric fields, we have the vector potential. And we didn't get rid of this guy, but we also now have the scalar potential. We have the gradient of the scalar potential. So this is just a mess. But remember that the field potentials, they are not defined uniquely. Instead, there is always a gauge freedom. So we can choose some certain gauge condition which these potentials will satisfy. And we're going to choose the Lorentz gauge, in which the scalar potential and the vector potential are linked by the following identity. So we're going to utilize, we're going to leverage the gauge freedom, which is the fundamental property of electromagnetism. And we're going to choose this gauge just because we can. We can choose any other gauge, but we do this because, as you'll see in a second, this makes our life much easier. So now if we use this gauge, this Lorentz gauge, we can finally use our beloved vector identity. We can expand the double curl of the vector potential and apply the Lorentz gauge condition. If you do this, we obtain the following simple equation, which we're going to be solving. This is much nicer than what we had previously. So first of all, this equation does not couple different Cartesian components of A, because the Laplacian, unlike the curl operator, when it acts on the x Cartesian component, it remains the x component, but it becomes the sum of different derivatives. The point is, you can expand, you can split this equation into 3 independent scalar equations for the x, y, and z Cartesian components of your vectors. And another nice thing is that if you consider certain Cartesian components of the current, for example, Jx, then this Jx will produce only the corresponding component of the vector potential, Ax. So if you have a source with the x components of the current density, then this thing will only produce Ax, and it will not produce Ay or Az. This is what allows us to split this equation into three independent scalar equations. And so we proceed and we write the scalar Green's equation for the scalar Green's function. The scalar Green's function, G naught, by definition, satisfies the following equation. So what we did is that we took this equation, the equation for the vector potential, and instead of J, in place of J, we plugged a delta function. This is what happened, minus delta function. And now we need to solve this scalar equation. So this is mathematical physics. I'm not gonna bore you with obtaining solution to that. We know that the only physical solution of this equation is the following, and this is an important expression. You should memorize it. It expresses the only physical solution of the Green's equation for the scalar Green function of the Helmholtz equation in free space. So physically, this is a divergent spherical wave which diverges from the source as a wave due to this exponential factor, and also decays as we go away from the source. I know that this combination, this expression, depends only on the difference. So if we have our point source here at R0, and this is our observation point given by R, then the value of the Green tensor depends only on this difference. So what we can do is that we can introduce a single argument function, G naught R omega, where R is simply the difference between these two arguments. Okay, so now we know this scalar Green function. How does it help us with finding solution to the vectorial problem? Well, we can calculate the vector potential produced by an arbitrary current density J by calculating this convolution of the current density with the scalar Green function. And remember, because equations for different Cartesian components of A, for AX, AY, and AZ, they decouple, and because AX only depends on the JX, we can write this in the vectorial form. So this, in principle, is the answer. This gives us the vector potential of an arbitrary current density. We know G naught, we know J. J is fixed by the problem, and in principle, nothing stops us from calculating this integral. And then we can calculate electric and magnetic fields, but there's a problem. Can anyone tell me what the problem is in these expressions?
We don't know this.
Yeah, we don't know the potential because the electric field is not only determined by the vector potential, it's also it has the scalar potential. And we haven't solved an equation for the scalar potential for phi. But we have fixed the Lorentz gauge condition. Remember that the potential, the scalar potential, and the vector potential are linked. We have already fixed that in the beginning. We assume that there is this relationship between the two, and we have fixed this relationship ourselves. So of course this is satisfied. And the moment we know A, and we do know A, we also automatically know phi. So from here we determine phi, we plug that back into this expression for the electric fields. It gets quite messy, but in the end, when you perform all the tedious math, all this exercise, you end up with the following elegant formula. So electric field is expressed as this vectorial operator. This is the unity matrix identity operator, and this is divergence of A, and we take the gradient of this combination, the divergence of A. This gives us the electric fields. And then also correspondingly, we can calculate the magnetic field as a rotor of the vector potential. So this, in principle, gives us the complete answer. Now we know the scalar Green's tensor. We know how electric field is related to the vector potential. So we have solved the problem. But now we can make one final step, just one cosmetic step that will allow us to write the answer in a more compact and in a more universal form. So what I'm talking about is that I want to introduce not only the Green's scalar function, G0, I want to introduce a tensor, Green's tensor, that will allow us to express electric field through current directly. And to that end, I'm introducing the following tensor. You can find the details of how we go from one to another, from scalar Green to tensorial Green in Novotny, for example. So the point is, this is the Green's tensor, and with use of this tensor, this is a 3×3 tensor, which contains these differential operators. We can write electric and magnetic field just in the way we want it. So we write them as volume integrals acting on the current density, and we convolute them with this Green's tensor. So the tensor, this differential operator, acts on the vector field, on the current. We integrate it over the entire volume, and that gives us electric field. And similarly to the magnetic field, where additionally we have to calculate the rotor of this monstrosity. Okay? So this is the final answer. This is the Green's tensor of the free space, which allows us to calculate electromagnetic distributions, electromagnetic fields of an absolutely arbitrary, well, at least finite current densities enclosed in certain finite volume V. So this is the coordinate representation of this Green's tensor in a Cartesian system, where this capital R is a rank 2 tensor, which is the direct product, or tensorial product, outer product of the radius vector R. And we talked previously what this thing is, and if you don't remember, the direct product is expressed as, in our case, this is gonna be a 3×3 matrix. This is x squared, y squared, z squared. Here is gonna have xy, xy, xz, and the corresponding symmetric combinations here. You get the idea. So this is an expression that sometimes you might gonna use to calculate electromagnetic fields of a point dipole or of certain arbitrary, more complicated distribution of electric current density. Okay? And we're gonna come back actually to this expression in a couple slides. Okay, so this is in principle the answer. This is the complete answer. So now we can apply these results that we just obtained to some practically common cases of emitting systems. And what can be easier than a point dipole, a point electric dipole? Oh, well, actually one step before we go to electric dipole. Another approach, another way to obtain the Green's tensor, another way to solve the same problem. So let's take the wave equation for the Green's tensor with the delta function on the right-hand side and do this partial Fourier transform of that. So we transform, partial Fourier transform means that all R's are mapped into K's. Just like time is mapped into frequency, radius vectors can be mapped into wave vectors. And if you do this, we're gonna obtain this. So double curl operator transforms to this, to k times g, where this curly g is the Fourier transform of our Green's tensor, which now depends on frequency and the wave vector, minus this guy equals identity. Identity operator is simply the Fourier transform of our delta function, because delta function in real space is getting mapped into just a flat function into unity everywhere And in the tensorial notation, this is a unity identity operator. And in principle, looking at this, it should be possible to resolve. We can group these G's and inverse the resulting operator and get this. So in principle, this is the answer. G, the Fourier image of G, can be calculated as the inverse operator of this combination. But the simplicity of this is very deceiving, because this involves not only calculating the inverse of the operator, which might be really, really tricky, but also you have to take this thing and calculate the Fourier image of this to get the real tensor in the real space, okay? And this may be very, very complicated. So bear in mind that the simplicity of this approach, the way we have done this in just 2 or 3 steps, is really deceiving. However, in some situations, this approach might be useful. For example, in the case of anisotropic media. If you were to use the previous approach, the way we solve the problem in isotropic medium in free space, if you were to apply that approach to, for example, a uniaxial or a biaxial or hyperbolic media, you would run into a problem. However, this approach allows us a very nice way to find the Green's tensor, at least the Fourier image of the Green's tensor in the case of anisotropic media. So to that sense, we simply plug epsilon here. So epsilon also appears here. And this is it. This is the answer to the Green's tensor problem in medium with an arbitrary anisotropy. You simply plug your tensor epsilon mu in this expression, calculate the inverse, well, which might be complicated, of course, but it can be done numerically. It is much easier and it is more transparent than trying to find the Green's tensor of an isotropic medium in the real space, where this problem is, well, it's much, much more complicated. So at least this offers some way of addressing the problem of radiation in anisotropic media. And from what I remember, this is how it's practically, how it's usually done in practice, solving the radiation problem with anisotropic media. Okay, so now let's go to the electric dipole. A point electric dipole is a point source located at some point in space, R0, and we can express this current density, J, of the electric dipole as minus psi omega, which comes from the fact that current density is dp over dt, where p is the polarization density. P is the vector quantity that characterizes our actual dipole moment, and delta is the delta function, because this is a point dipole. And we usually express the electric and magnetic fields via the dipole moments in the following way. So P is our dipole moment, G is the Green tensor of free space, and then we have the wave vector and permittivity of free space. So now we can plug the Green's tensor that we found previously and study the results in electric and magnetic field distributions. So just for reference, here I'm showing you the explicit expressions for the electric and magnetic field of an arbitrary polarized electric dipole. This can be linearly polarized dipole, circular polarized dipole located anywhere in space. This is just for the reference, because this you're going to use quite frequently if you're going to study, well, any theoretical problem of nanophotonics. This is one of the important expressions that is very useful to have at your desk, or usually. So this monstrosity is the electric field. This is the spherical wave, and then this is the combination of different vectorial tensor products with different powers of K and R, which comes from this differentiating operator, the tensor G, and magnetic field has a similar structure. And in this expression is the unit vector directed towards the observation point from the source. So this is the snapshot of the electric field, of the instantaneous value of the electric field created by a source polarized along the z-axis, located at the 0 points of our Cartesian system. This is the x component of the electric field. This is the z component of the electric field. So, well, this is the typical structure of the electric field of a point dipole. We can see this spherical wave diverging sort of away from the dipole. We see this phase fronts. And, well, the field, of course, is much more intense close to the dipole because it's getting concentrated around the dipole, and it decays fairly quickly as we go away from the dipole to infinity. And let's inspect in a bit more details how this decay of the field in space actually happens for a point dipole. So let's first look at what happens to the electric fields in the near field zone, where we look at the field at spatial scales much closer to the dipole than the wavelength of the emission. And if you look at the electric field magnitude, which is plotted here on the log scale, this is log of magnitude of electric field, total magnitude, x component plus y component plus z component. So this is what we're going to see. Again, we have a z polarized dipole sitting at 0, x, y, z equals 0. And this is the electric field magnitude, log scale. So as you can see, it decays very rapidly as we go closer to the source, and it decays very rapidly as we go away from the source. And one particular feature of this plot is that, as you can see, the field tends to concentrate along the vertical axis. So here, around the poles, the field is more concentrated, is more intense than on the equator of the sphere. Okay, so you can remember from this picture that in the near field of the dipole, the field is more intense on the axis of the dipole. However, if we look now in the far fields, where the distance from the dipole is much greater than the characteristic wavelength of the emission, the opposite situation happens. Now on the axis of the dipole, we have nearly zero field. The decay is much faster. But instead, the field tends to concentrate along the equator plane of the dipole. So the field is actually radiated in the z equals 0 plane, in contrast to the near field situation. So this is the characteristic spatial behavior of the electric field in the near field and in the far field. And another way to understand this, we can understand this by actually expanding the electric field of a point dipole in the near field zone. And if we keep only the highest power in the expansion, we keep only 1 over r cube power for the electric field and 1 over r squared power for the magnetic fields. And we neglect all other terms, which behave much slower in the vicinity of the dipole in the near field zone. We obtain this for electric fields and for magnetic fields. And if you look closely at the expression for the electric field, you're going to notice that this actually looks like electric field of a static dipole. There is no frequency, there is no wave vector here in this expression. There is only the distance from the dipole moment, and the vacuum permittivity. There is no frequency, so this is a static, the fields of a static dipole essentially. Magnetic field is different. Magnetic field does have frequency because, well, the magnetic field of a static dipole is 0. So if we want to look at the magnetic fields in the near field zone, we have to include certain frequency. But the important point is that the electric field of a point electric dipole in the near field zone exactly coincides with the field of a static dipole. And then we can do similar exercise in the far field zone, where Kr is much greater than unity, and we'll obtain these two approximations for the magnetic and for the electric field. And what is interesting about these two approximations is that both the electric and the magnetic fields are purely transverse, so that is, they are perpendicular to the radius vector in the far field zone. Okay, this is not true generally in the near field zone. The magnetic field is perpendicular to the radius vector, but the electric field is not. For example, electric field at the poles of the dipole is collinear. Electric field is collinear with the dipole axis. But in the far field zone, electric field and magnetic field are strictly perpendicular to the observation direction. So this is another way to visualize the difference in the spatial field dependence in the far field and the near field zone. We can plot the field amplitude, the field magnitude along certain direction as a function of kr, and we can clearly see the 1 over r cube dependence in the near field zone and 1 over r dependence in the far field zone as predicted by these expressions. And here's a short but useful exercise for you. Consider doing it at home. So you can obtain these different expansions, these different parts of the green tensor by splitting the green tensor itself, the full green tensor, into 3 components by keeping different powers of the expression. You can keep 1 over r cubed, you can keep 1 over r squared, and you can keep 1 over r. And by grouping the terms in the full expression according to these powers, you can obtain 3 different components of the green tensor corresponding to the near fields component, to the far fields, and to the intermediate fields, which will contain the 1 over r squared component, and which will be present somewhere here, as the title suggests, as the name suggests, in the intermediate region between the near and the far fields. So now let us look at the radiation pattern of a point dipole. To that end, let us calculate the power that the dipole emits in a narrow angular range. So let's say this is our dipole, and we go far away from the dipole, and we look in a narrow solid angle d omega, and we calculate the total energy flux carried by the electromagnetic field through that narrow angular segment. And this is done by calculating the Poynting vector and by multiplying this Poynting vector by the area of this solid angle. That's it. So if we utilize the expression for the electromagnetic field that we obtained previously, we'll obtain the following directivity pattern. So the pattern, the power that goes into solid angle d omega is proportional to the 4th power of the frequency, to the square of the dipole moment, and to the square of the sine of the angle. And if we were to plot this directivity pattern, we would obtain the following shape that I'm sure most of you recognize. This is the famous closed directivity pattern of a dipole. So we have a point dipole here, aligned along the z-axis, and the distance of that shape from the dipole corresponds to the intensity radiated by the dipole in the corresponding solid angle diameter. So this distance is proportional to the intensity. And from that, you can clearly see that the dipole radiates most of its power in the plane, in the horizontal direction, this sort of, okay, horizontally and not vertically. It radiates exactly 0 intensity along its axis. And this is in accordance with the pictures that we already saw. If you recall the pictures with the electric field magnitude in the far field zone, you remember that the electric field of the dipole in the far field zone is essentially 0 along its axis. And this is reflection of the fact that the directivity pattern of our dipole has such torus-like shape with 0 intensity emission along the axis of the dipole. So now let's take this expression one more time for the angular distribution of the intensity of the dipole, and let's integrate it over the solid angle diameter of the entire sphere. And if we do this integration, we'll obtain the famous formula. Нет, все прекрасно работает. So we're going to obtain the following famous formula, the Larmor formula, that describes the total emission intensity of a point dipole in all directions, the integral emission intensity into all directions, which is proportional to the square of the dipole moments and to the fourth power of the frequency. So as you can see, as long as the dipole moment is fixed, the magnitude of the dipole moment, the emission intensity grows quickly with frequency. And this is the explanation of the blue color of sky, as you may know, because this suggests that the high energy photons experience much more intense scattering as they traverse through our atmosphere, and they scatter in all possible directions simply because the scattering intensity, the emission intensity of the scattering emission of high energy photons on the particles in the atmosphere is much higher. So the probability for the blue photons to scatter is much higher. And that is why they occupy all possible directions on our sky. And it looks like they come from all possible directions. Whereas low energy photons that carry red, orange, and yellow color, the probability of these photons to scatter on the same dipoles is much lower. And this is why they travel in nearly straight lines. And this is what gives the sky blue color. We can, by analogy, we can do the same exercise for a point magnetic dipole. We replace electric dipole with a current loop, with a sub-wavelength, very small current loop. This gives us a point linearly polarized magnetic dipole, and we can ask, okay, what are the formulas that relate this magnetic dipole moment to electric and magnetic field at a certain observation point? And our goal is to write the induced electric magnetic fields in this way, where these units in front of the tensors were chosen such that the electric green tensor that we obtained just a few minutes ago and the magnetic green tensor here, that they have the same units. This is why we chose these constants here in this particular way. And you can find the derivation in Jackson, in Landau. I'm not going to do this tedious exercise right now, but if you perform the exercise, you're going to find that in free space, magnetic green tensor and electric green tensor are identical. They are the same. And if you think about it, it makes perfect sense. And it is a simple consequence of duality of electromagnetic field in free space. So duality, as you might remember, is a property of Maxwell's equations, is a certain symmetry of Maxwell's equations that admits replacing electric fields with magnetic fields in the absence of media, in the absence of sources, in the absence of currents and charges. And when we do have media, you may remember that there is a certain generalization of duality when electric field is replaced with magnetic field is replaced with minus electric field, and we also need to have the impedance here. I think it's Z here, and it's Z impedance here. But we also need to replace permittivity with permeability and permeability with permittivity. And so there is a similar generalization of duality in the presence of sources. So what we need to do is that we need to replace all electric sources with magnetic sources, meaning that electric dipoles are replaced with magnetic dipoles and vice versa. And that should, at the same time, replace electric field with magnetic fields. And when you think about that in such a way, it becomes sort of obvious that the electric and magnetic green tensor must be equal in free space, because the free space is, of course, dual with respect to such a permutation. And that will have certain consequences later when we when we introduce the concepts of the local density of states, electric density, magnetic density of states, and we're going to see that duality plays a very interesting role there as well. Okay, so that was the Green's tensor for you, electric Green's tensor, magnetic Green's tensor, and also the fields of a point dipole. But we don't always have such simple sources. Sometimes sources of electromagnetic field are more complicated, quite more complicated. These sources can be very complicated distributions of electric current density, and they also can have certain charges. And usually these charges and currents are enclosed by some finite volume V. And often the problem is to find the fields radiated by these currents, or at least try to classify, to quantify these fields produced by a very complicated distribution of charge and current, to classify them, to quantify their angular distribution. And this is what we're going to do in the next few slides. So consider certain distribution of charge and current density located, confined to certain volume V, and this charge and current are, of course, related by the continuity equation. They cannot be absolutely arbitrary. They are related. Once we have the current density, we automatically obtain the oscillating charges from the continuity equation. And given this current distribution, we can always calculate the radiated electric and magnetic field by using the Green tensor. We assume that the structure is just free space. There is no structures, no media. There are only certain currents. So this is the Green tensor of free space that we already know. And well, that would be quite complicated to do this exercise every time for any charge and current distribution. And we sort of would have been blind in the situation, because so what we want to do is that we want to have certain tool that will tell us, looking at a certain current distribution, that will tell us, okay, this thing radiates almost like a dipole. This thing radiates like a magnetic dipole. This thing radiates like a quadrupole, and so on and so forth. So what we want to develop is a certain tool that, given certain electric current density, will tell us what this current distribution looks like in the far field, what field it creates. And we're going to apply the formalism of vector spherical harmonics that we very briefly studied a few lectures ago. So what we're going to do is we're going to expand this radiated field and H into spherical harmonics, and then we're going to relate the amplitude of different spherical harmonics by using only we're going to relate this amplitude to these localized current densities. And we're going to obtain a series of expressions that allow us to plug the current density into certain integral equations and to tell us, to see which multiples, which spherical harmonics we actually have in this radiated field. Do we have dipole harmonics, quadrupole harmonics, electric, magnetic, or something else? So this is how we're going to do this. Yeah, this is just a reminder of what spherical harmonics are. These are scalar spherical harmonics, which are characterized by two indices, L and M. L is called the longitudinal, the orbital angular momentum index, and M is the projection of that index on the Z axis. And spherical harmonics satisfy the orthogonality property. And this is the visualization of the first few lowest scalar spherical harmonics with indices L ranging from 1 to 10, and also different M's plotted on the surface of a unit sphere. So this is just the angular dependence of the spherical harmonics to remind you what they actually look like. So this is corresponding to the monopole, the dipole, the quadrupole, and so on and so forth, spherical harmonics. Okay, so now we need to expand these fields into spherical harmonics. Spherical harmonics form vector spherical harmonics, form a complete set in free space. So we can calculate the radiated fields using the Green tensor, and we can calculate the overlap integral of the radiated field with a particular spherical harmonic, scalar spherical harmonic. And that overlap integral gives us, in principle, the sought for amplitude of AT and ATM, where AT is the amplitude of the transverse electric harmonic and ATM is the amplitude of the transverse magnetic harmonic. So G and F should be the Hankel functions, spherical Hankel functions that describe the radial dependence of the fields. And this can be Hankel functions of the first and second kind, corresponding to the outgoing. So H1 corresponds to the outgoing harmonic, and H2 corresponds to the incoming harmonic. Because we don't know yet if this field contains only outgoing divergent fields or if it also has certain incoming fields. And in the end, we're going to have 4 integrals for 2 polarizations and 2 kinds of Hankel function that fully determine the amplitudes of all divergent and convergent spherical harmonics. But often we are dealing with the field that contains only divergent, because if our surface V, if our charge distribution is located completely inside, is completely enclosed by the surface dV, then outside the surface, the field must be purely outgoing. We cannot have any convergent harmonics because there is nowhere for these harmonics to converge from. They must be outgoing. And so these functions F and G must be, in this case, must be described by the Hankel function of the first kind, and we obtain only 2 integrals. Now we can plug this electric and magnetic field via the green tensor and the current density, and then this is a very, very tedious, very technical exercise, but after you do all the steps, you end up with the following volume integrals. So this is just the volume integral. There is no contour integral. The volume integrals over the entire region V of the entire source area, that inside they have very complicated combinations of spherical harmonic multiplied by this monstrosity, which contains current density, which we do know, the charge density, sorry, and the current density, which we also do know. And this, in the end, after we perform the integration, gives us the amplitude, a particular multipolar amplitude. So what you need to do is that you need to choose a particular polarization, transverse electric or transverse magnetic, a particular L and a particular M. Plug these indices into the integral and calculate the integral. And that will give you the amplitude of the corresponding spherical harmonic. So by calculating these integrals, you will know for absolutely arbitrary distribution of electric current density, you will know what your field looks like, whether it's a field of an electric dipole, of a magnetic dipole, magnetic quadrupole, electric octupole, and so on and so forth, without calculating the radiated fields. Notice that here you have only the current densities. You don't have the electric field, you don't have the green tensor. You don't need to run these crazy calculations for the electric and magnetic fields. You don't need to calculate green tensor times current density. We already have done this inside these formulas. Here we have only one integration. You multiply the spherical harmonic by this, well, pretty complicated combination, but still you don't have green tensor. You don't have the intermediate step. Just by doing one integration, you obtain the amplitude of the spherical harmonic. This is it. So this is the answer. This is the tool that we wanted to develop, which, given any distribution of the current density, spills out a complex amplitude of the harmonic. Now, in certain situations, the dimension of the source area where the charges and currents are confined are much less than the wavelength of the radiation. This is called the long wavelength approximation, when this quantity is much less than 1. And K is the wave number of the radiation, and R is the radius of this sphere that completely encloses all sources of radiation. And in this case, what we can do is that we can expand these Bessel functions, J, we can expand them into Taylor series. So J0, J1, J2, and so on and so forth. We can expand them all, and because this is the sub-wavelength, long wavelength approximation, they will give a satisfactory result inside our sphere of radius r. So we have certain currents, and if the wavelength is huge, then these approximations will work just fine, and we can apply them to calculate our integrals. So this is called the long wavelength approximation, and sometimes it becomes quite useful because in many practical situations, this is the case. The source or the source currents are indeed confined to a sub-wavelength region in space. And why not simplifying our life if we can do that? And now if we apply this long wavelength approximation to the electric dipole harmonic, to the TM1 harmonic, spherical harmonic, we can obtain a vector with 3 Cartesian components. So this is which is related to the amplitudes of 3 spherical harmonics. So the z component of this vector will represent the 1, 0 spherical harmonic. And this combination, mu x plus minus I mu y, will give us these 2 amplitudes. So for TM1, we have 3 possible harmonics. We have TM 1 minus 1, 1 plus 1, and 1, 0, 3 spherical harmonics. And we have correspondingly 3 Cartesian components of this thing. So now let's try to understand what these 2 terms mean. These 2 terms originate from the expansion of the Bessel function in this Taylor series. So we had this spherical harmonic, we had the Bessel function. What we did is that we expanded this into Taylor series, and we obtained these 2 integrals, and you already may recognize at least one of them. The first term, is called the Cartesian electric dipole. This is simply the volume integral of the current density over the entire source region. This is just the volume integral of the current. It does not involve any Bessel functions, no spherical harmonics, no nothing, just the integral. And this is the electric dipole that describes simply the static dipole moment of any distribution of currents and charges. This is the dipole moment that you know from the second volume of Landau-Lifshitz that they introduced in chapter 2 or 3, I don't remember. So this is just static dipole moment of certain subwavelength distribution of charges, which is directed from minus to plus, nothing else. And so it means that this guy, this contribution, this expression describes to a certain extent the amplitude of the TM10 spherical harmonic. This integral is one of the contributions that describe the transverse magnetic spherical harmonic. It's 3 components with different indices n. So now you might ask, well, what's the remaining term? What's the second question? What's the second component in this expression, which doesn't look like a familiar electric dipole? This is something else. This is something more complicated, and it is referred to as the toroidal dipole. So this is the this contribution, which also looks like a volume integral, and it is. But it not only involves current density, it also involves certain dot products and multiplication by the radius vector. And because it enters the same formula, it enters the formula for the coefficients of the same exact spherical harmonic, it describes, it contributes to the amplitude of the same spherical harmonic, but it originates from the different charge distribution. So if electric dipole originates from current flowing around along the straight lines inside our region V, the toroidal dipole, which is described by this integral, originates from completely different geometrical features of the current. So toroidal dipole describes electric currents flowing around a toroidal surface. So imagine that you have a torus, and on the surface of that torus, there are electric currents that flow perpendicularly to this ring, okay, along these lines. And such a current distribution, when you reduce the size to subwavelength area, that will produce a toroidal dipole. But what's interesting is that this toroidal dipole contributes to the very same spherical harmonic. In other words, the far field that the toroidal dipole produces is identical to the far field produced by the electric dipole. So despite the fact that these two Cartesian dipoles are described by different formulas and they originate from different distributions of electric current and charges, they produce identical field, identical electric and magnetic field outside the source region, not only in the far field, but everywhere in space. Everywhere in the space, they're indistinguishable. If you look outside the source region, you cannot tell if you have an electric dipole, a Cartesian electric dipole formed by just straight lines of currents, or if you have a toroidal dipole with electric currents flowing around the torus. They're completely indistinguishable, and the total field created by electric dipole and toroidal dipole in the long wavelength approximation is just the sum of the two. It is just the sum. And of course, these are just the two lowest order terms from the full expansion of the ATM one harmonic. There are other terms, there are higher order terms that contain higher powers of R, but we're not going to cover them, that also produce identical fields outside V, outside the source region, but originate from completely different structures of current. So what it means is that you can have quite different geometrical structures, quite different distributions, microscopic distributions of currents that are in a way orthogonal and look completely different, yet they produce indistinguishable electric and magnetic fields outside the source region. And that leads us to a very interesting possibility. It leads us to the possibility of non-radiating sources. So in this particular example of electric dipole and toroidal dipole, imagine that we have certain combination of electric dipole and toroidal dipole. And as we just saw, the full amplitude of the corresponding spherical harmonic is described simply by the algebraic sum of these two guys. And it may happen that this sum will turn to exactly zero, because it can, if the phase and amplitude relationship between these two terms is appropriate, the sum may be zero, which means that the amplitude of the corresponding spherical harmonic will be zero too, which means that this combination of electric dipole and toroidal dipole does not produce any field outside at all. Their field is indistinguishable. They interfere destructively. Ideally, there is no field, yet because their microscopic structure is different. The microscopic structure of currents responsible for P and for T is different. They do not interfere destructively inside. They are still described by some non-trivial current distribution J, which does not equal zero. This is some non-trivial electric current density which does not vanish, yet it produces exactly zero fields outside. So this is a non-radiating source. Certain non-trivial distribution of current density, which, thanks to the destructive interference, does not produce any field at all outside, but it is characterized by some harmonic, monochromatic, oscillating electric currents contained in a certain region. And this particular example, where the non-radiating source, where the radiation is cancelled because of the interference between electric dipole and toroidal dipole, is referred in the literature as the unipole source. Like I said, the origin of the destructive interference, the origin of this non-radiating source is the destructive interference between two Cartesian dipoles that have different microscopic structure inside the small area where the currents are located, and identical field patterns that interfere ideally destructively outside the source region. And there are, of course, more complicated examples of non-radiating sources. There are higher order unipoles, there are magnetic unipoles, quadrupole unipoles, and so on and so forth. But the underlying abstract description of these non-radiating sources is identical. They have different microscopic structure inside, but identical field patterns outside that cancel each other. So this is the non-radiating sources in essence. And that brings me to the end of today's lecture. So that was pretty short, just like I hoped. So today we started with you looking at the radiation problem. We derived the Green's tensor of free space both in the direct R space and in the Fourier space. We studied the fields produced by point electric dipoles in the near fields and in the far fields. We calculated emission intensity of the dipole. We introduced the multiple expansion of an arbitrary radiating system and discussed the phenomenon of non-radiating sources. That's all for you. See you next week. Thank you for your attention.